What specific problem does your proposed latent variable model address regarding the interpretation of large language models, LLMs? Can you explain the significance of this problem in the context of existing research?
The proposed latent variable model addresses the problem of understanding how large language models, LLMs, can learn and represent human-interpretable concepts through next token prediction, challenging the prevailing view that LLMs operate primarily through memorization. This model is significant because it provides a framework that captures the generative process of language data, while allowing for complex relationships between latent and observed variables, which existing models often overlook due to strict assumptions like invertibility. By demonstrating that the representations learned by LLMs can be approximated as a linear transformation of the posterior distribution of latent variables, the model offers theoretical support for the linear representation hypothesis, which posits that concepts in LLMs are encoded linearly. This connection is crucial as it bridges empirical findings with a theoretical foundation, enhancing our understanding of LLM mechanisms and their potential to model aspects of human intelligence. Overall, this work contributes to the ongoing debate about the nature of intelligence in LLMs and provides a more nuanced perspective on their capabilities beyond mere data memorization.
How does your proposed method or algorithm work? Please illustrate it step by step, particularly focusing on the connection between latent and observed variables and the role of next token prediction in this process.
Our proposed method utilizes a novel latent variable model to capture the text data generation process, where latent variables represent human-interpretable concepts and observed variables correspond to words. The process begins with next token prediction, where the model predicts the probability distribution over the next token, output variable, y, given a context, input variable, x. This prediction is achieved through a softmax function applied to logits from the model's final layer, effectively approximating the true posterior distribution of tokens. We establish a connection between the latent and observed variables by applying Bayes' rule, allowing us to express the true posteriors of the latent variables conditioned on the input tokens. Our identifiability analysis shows that, under certain conditions, the representations learned through next token prediction approximate a linear transformation of the logarithm of the posterior distribution of latent variables. This indicates that next token prediction not only facilitates the learning of token distributions, but also enables the model to capture and represent underlying latent concepts, thereby linking the observed outputs back to the latent variables effectively.
Can you provide a simple yet illustrative example demonstrating how your algorithm captures the relationships between latent concepts and observed tokens in the context of language data generation?
An illustrative example of how our algorithm captures the relationships between latent concepts and observed tokens can be seen through the concept of gender representation in language. For instance, consider the latent concepts represented by the words man and woman. Our model posits that the difference in their representations can be approximated as a vector offset, where the representation of man minus the representation of woman is similar to the representation of king minus the representation of queen. This demonstrates that the latent variable model effectively encodes human-interpretable concepts linearly, allowing for manipulation of these concepts through simple vector arithmetic. Additionally, when we apply linear probing, we can measure the probability of an output being in a specific language, such as French, which is logit linear in the representation of the input. This showcases how our algorithm not only identifies latent concepts, but also captures their relationships with observed tokens in a coherent manner, aligning with the linear representation hypothesis.
What are the theoretical or practical benefits of using your latent variable model over existing approaches to understanding LLMs? How does it improve interpretability or efficiency?
The theoretical benefits of our latent variable model include its ability to capture the complex relationships between latent human-interpretable concepts and observed variables without imposing strict invertibility constraints, which aligns more closely with real-world data. This flexibility allows for a more accurate representation of the generative process underlying language data, enhancing the model's interpretability by providing a clearer connection between latent concepts and their observable manifestations. Practically, our identifiability analysis demonstrates that representations learned through next token prediction approximate a linear transformation of the posterior distribution of latent variables, offering a unified perspective that supports the linear representation hypothesis. This connection not only enhances our understanding of how LLMs encode concepts, but also facilitates the manipulation and probing of these concepts, thereby improving the efficiency of tasks such as concept extraction and modification. Overall, our model provides a more nuanced framework for interpreting LLMs, bridging the gap between empirical observations and theoretical foundations.
How did you validate or test the effectiveness of your proposed model? Please discuss the experimental design, the datasets used, and the metrics you employed to demonstrate the model's performance.
To validate the effectiveness of our proposed latent variable model, we conducted experiments on both simulation data and real data across various model families, specifically Pythia, Llama, and DeepSeek R1. The experimental design involved assessing how well the representations learned by the models aligned with our theoretical findings regarding the identifiability of latent concepts. We employed metrics that focused on the accuracy of next token predictions and the degree to which the learned representations corresponded to the linear transformation of the posterior distributions of latent variables. The results from these experiments were consistent with our theoretical insights, demonstrating that next token prediction is sufficient for learning a deep understanding of the data, thereby supporting our claims about the model's performance. This comprehensive approach allowed us to empirically substantiate the connection between our model and the linear representation hypothesis.
What specific results did you achieve with this latent variable model in your experiments? How do these results contribute to the conversation about the linear representation hypothesis in LLMs?
In our experiments with the latent variable model, we found that the representations learned by large language models, LLMs, approximate a linear transformation of the logarithm of the posterior distribution of latent concepts, supporting the linear representation hypothesis. Specifically, we demonstrated that the learned representations are equivalent to a causal model of the observed data, up to a linear transformation, which indicates that next token prediction can effectively capture human-interpretable concepts. Our results were consistent across various model families, including Pythia, Llama, and DeepSeek R1, reinforcing the idea that LLMs encode concepts linearly. Furthermore, we established a unified framework connecting different manifestations of the linear representation hypothesis, such as concepts as directions and concept manipulability, through the linear transformation matrix derived from our identifiability analysis. This contribution not only validates the linear representation hypothesis, but also provides a deeper understanding of how LLMs can learn and manipulate human-interpretable concepts.